Hello everybody, welcome back to this short course on quantum computing. Today, we'll be continuing our discussion on superconducting qubits. So let us go through a very quick recap of what we had discussed in the previous lecture. So in the previous lecture, we had talked about a two-level atom, which is two discrete energy levels denoted by ket0 and ket1. These are the energy eigenstates, separated by an energy delta E, which is basically proportional to omega 01. There is a frequency difference between these two energy states. Now, when we drive or excite this two-level system with an external electric field, which is a function of T, what happens is that oscillation between the level 0 and 1 begins. That's called Rabi oscillations. In other words, the probability amplitudes evolve as oscillating functions with time. So this oscillating frequency is proportional to the strength of the microwave pulse that is driving the system, which is called the Rabi frequency. And this whole phenomena is called Rabi oscillations. So as you can see, the blue color curve shows the probability of occupancy of the particle at energy 0, which is the ground state, at time 0 is equal to 1, and nothing is present at the excited energy state. So when we start driving the system, the probability of occupancy of the ground state decreases sinusoidally, and the same for the excited state increases sinusoidally. With time, we reach a point where the probability of occupancy in both of them are equal, that is equal to 0.5. And then at certain instant, the probability of occupancy of the ground state becomes 0, and that of the excited state becomes 1. And if we apply a pulse of time width equal to the omega times tau is equal to 2 pi, in that case, we are able to swap the populations of occupancy of the ground state and the excited state. So that is how we are able to control the two-level system by applying a pulse, a drive, and making some sort of oscillations, and oscillation frequency depends on the strength of the drive, and the duration sort of decides the function of the drive. Now, what we can see from here is that we can sort of manipulate the two-level atom system by applying such a drive through Rabi oscillations. We had discussed about these concepts in the previous lecture in details. Now, the question is, how do we physically realize these two-level atoms? I mean, in nature, whichever atoms you find are not two levels. They have separate energy levels. So what we do is that we sort of take an LC circuit and apply quantum circuit electrodynamics on it, as a result of which the flux quantity is phi, I is the current flowing through the circuit, V is the voltage across a capacitor, C and L. Now, when we find the Hamiltonian, that is the total energy of the system, we get this expression. So it's a sum of the electrically stored energy, because it's a resonant circuit. So energy stored in front of magnetic fields in the inductor and the electric fields in the capacitor. And the energy kind of gets exchanged, keeps on getting exchanged between these two. And if we have no resistive element in such circuits, this oscillation does not get damped out with time. And that's the ideal scenario. So this is the capacitive energy, and this is the inductive energy. So EC is the energy related to the storage of charge in the capacitor, and EL has to do with the storage of magnetic fields or magnetic energy in the inductor. So these are quantized quantities, and n square is basically, n is an integer and phi is a quantized quantity. So this is called quantized flux, and this is called quantized charge. So we won't get much into the details of these things at this stage, at least. So basically what we can see is that this sort of a quantum circuit acts as a quantum harmonic oscillator, which with different energy, discrete energy levels separated equally from each other, and many such discrete energy levels can exist. And this potential function, this parabolic potential function, is similar to that of classical case of a mass spring system. However, the energies were not discretized in that case. Now remember, we want to implement a two-level atom, but then here what we see is that we have several such energy levels present, right? How do we extract only these two energy levels out of this whole system? Can you just give it a thought? If we want to operate between these two energy levels only and not go into these energy levels, what is the criteria? Can you just give it a thought? Can you just pause the video and give it a thought? All right. So basically, when we apply a drive of frequency omega r, it can cause transition between any of these states, because all these energy states are equi-separated by h cut omega r. And if I apply a drive of omega r, not only I'll be driving a transition between 0 and 1, can also drive a transition between 1 and 2 and 2 and 3 and so on. And you won't have an effective two-level system in that case. So what we do is that we keep the whole circuit same. We just make this inductor non-linear in nature, right? So the non-linear inductor is made using something that we call a Josephson junction, basically, which is made of a superconducting loop with an insulating gap in between. And this acts as a non-linear inductor. And instead of a parabolic function, we have a cosinusoidal function, as a result of which this anharmonicity takes place and the energy gap goes on decreasing as we go higher and higher up the energy axis. So if I have a drive that is equal to omega 0, 1, I'll be effectively operating between these two computational states, ket 0 and ket 1, and 1 and 2, 2 and 3 are neglected in that case. So this is how we actually don't have a precise two-level atom in nature, but we artificially simulate this kind of two-level atom using a non-linear LC circuit in the quantum environment. Now, the thing is that we want to use a superconducting material to make this stuff, because for the reasons that we had discussed in the previous lecture, because we don't want the Rabi oscillations to damp out before my algorithm or my pulse function is over. So they will die down nevertheless, but we should make sure that they die down after our algorithm is done, right? So this is what a superconducting qubit looks like. It's very simple looking structure, basically. So this cross basically acts as a capacitor CQ, and which is basically due to a lot of this capacitance arises due to a lot of factors, which we can, for the time being, not go much into the details of it. I could very well do that in one of the later lectures, but for the time being, this is one capacitor, and then this is basically a Josephson junction, and this is how you have this non-linear LC circuit. And what we have is that we have control lines, feed lines called XY control line or Z control line, and we have a readout resonator. We'll be discussing the function of each of these. So basically, this is the qubit, this non-linear LC, including the Josephson junction. Now we want to be able to manipulate it, right? We want to drive it by some external pulse. And basically, we have seen that the application of an external pulse, time varying pulse, causes oscillation. That's called Rabi oscillation. And depending on its strength and the duration of the pulse, we can kind of set different values of C1t and C0t, which basically the extent of rotation in this block sphere, as you can see, or pointing the arrow towards any other direction, is done by these control signals. So basically, this can be visualized, this whole picture can be visualized as a block sphere. And what is our objective is to change the direction of this arrow and point it towards the direction we're interested in. And that is how we do it using the control lines. So XY control line gives a microwave pulse whose phase is such that a rotation happens around the XY axis, and Z control pulse is such that the rotation happens across the Z axis. So these are two different functions. And that is how we can tailor the block sphere by applying an external pulse drive. And now the question comes is that how do we read out, like how do we interrogate the qubit as to what its state is? So we do that in a very simple way. We kind of couple this qubit to a resonator. It's called a readout resonator. And what we do is that this is the coupling resonator, readout resonator. We couple it capacitively with the qubit. And then there is a source of electromagnetic wave that is circulated to the resonator. Now, since the resonator is coupled with the qubit, the resonant frequency omega r of the qubit, of the resonator will be different depending on whether the qubit is in zeroth state or the excited state, in the ground state or in the excited state. And so what happens is now we have a source which is giving A1 pulse or signal, which is being circulated to the resonator, and we have a reflection back from here, which is circulated to the load, and we measure the reflected signal. The phase and the amplitude of the reflected signal will be different based on whether the qubit is in the ground state or is in the excited state. And that is how we can perform this readout. So as you can see, there's a setup which kind of sends an RF signal to the qubit through a resonator, and the reflected power or the signal S11, its phase and magnitude will be different based on whether the qubit was in the 1 state or the 0th state. And that is how we can detect the state of the qubit, right? So this is how we control and we manipulate and we read out a qubit. And this was all about the physical realization of qubits. I request you to now take a pause and sort of get yourself together to understand what's happening and appreciate what's happening over here. And if you are having some difficulty in understanding anything, you may rewatch this lecture. Also, there are other contents available on the internet, and you can go through those before coming to the next lecture, right? So this was about the physical realization of superconducting qubits. Thank you very much for watching. I hope to see you in the next lecture. So thank you very much.